actual two separate courses.
Like
Okay.
in
We have a question, guys?
it just looks like, because here you said it was 26 for the pi electrons, but it looks like you did, like how you got it on the quiz, you did the DUS times the 2 for each electron, but you can go back and look at the.
No, you would not do DUS for pi electrons.
Okay.
DUS is not related to pi electrons, I don't think. Look at the structure for pi electrons. Let's talk about it at another time because it's a very detailed, I need to look at what's going on. Let's look at it outside of class, okay?
Okay.
Okay, we need to finish up the acid base. Let's finish that up and then we'll get back to conformations. Acid base, acid base. Okay, how do we do on this one? We got this shown yet? Product of this drug reacting with HCl. Somebody have it? Very nice. This is incomplete though. You want to complete, total complete there. Anything that has charged, if the charged atom, I want you to show it very complete. That is all lone pairs. Okay. Looks good. Okay. Anybody up? Yeah. Yeah, why did you draw that line dash? I don't know if you meant to do that. I think those are right. I look quick. Sometimes I look and I don't see something. Let's do it here. Basically, here's your acid, right? Where's the base? What's the most basic atom? Did we talk about neutral nitrogens? Only thing neutral is going to be a good base tends to be nitrogen. Neutral oxygen is not a good base. Okay? There's only one base here. It's here. You don't even have to decide which nitrogen is most basic. That nitrogen lone pair is sp3 orbital. It's a good, decent base. These electrons do what? They take the H and they can bond to the H. These electrons move here. There's 3 there to begin with. What do we get? That nitrogen is bonded to 2 methyls, which are CH3 groups, right? It's now bonded to an H. I'm just cutting that off so I don't have to redraw the whole molecule. The nitrogen is now positively charged. Please place the charge right next to the atom. Maybe in Jenkins you put the charge up here in the corner or something. Don't do that. Right on the atom. Okay? And then what else we got up here?
CL.
Cl minus, because how many lone pairs does it have? It had 3. What does this arrow mean? The bonding pair is moving on to the chlorine as a lone pair. 4th lone pair, that's what that means. And that's a minus. This is the hydrochloride salt of the drug. Because it's a salt. What's a salt? Ion pair. Okay, there's your ion pair. We call that colloquially a salt. It's a salt that was made by reacting with hydrochloric acid. We call it the hydrochloride salt. Okay? Drugs are typically given as salts. Why? So they're more soluble in your body. I assume you have a lot of water in your body. Aqueous, blood, stomach. They're given as salts, so they're more soluble in water, so they'll dissolve easier. Sometimes it also makes them a little bit more stable. Sometimes lone pairs are might do other chemistry while it's sitting there on the pharmacy shelf. But now that it's protonated, it's going to be maybe more stable. There's a variety of reasons. The most common reason is it's more soluble. Which is more soluble in water, the neutral drug or the positive nitrogen protonated drug? It now has an ionic portion there. More soluble in water. hopefully pretty straightforward. You know your acid-base mechanism. It works for every acid-base reaction you could ever think of. There it is right there, yeah? Okay, hybridization effects. Alkaloids. Predicting acid-base equilibrium. Okay, let's pick up where we left off at, which is we did succinimide. How about the next one? How did we do? I expect that you have done these, attempted these, so that when we talk about them in a fairly quick manner, you'll be able to be familiar with them, have tried them, maybe ask your question, if it's kind of a quick question, et cetera, et cetera. If you've not really looked at it, then you're probably not going to get the most out of the discussion that we're fixing to have. I believe this is the one we're on, yeah? Okay, it's acid-base. What's the acid-base reaction? What's the most acidic H on the board? I got CH's, I got CH's, I got an OH. Where would you rather make a minus at? Yes, this is your acid right here. This is the acidic molecule. Let's draw that bond out. It's condensed. We need a bond if we're going to do a mechanism. And you should always do mechanism. So I'm going to draw that out. That's the acid. Hopefully that over there is the base. Or it ain't nothing. Is that a base over there? Do you see a base? Yeah, sp3 nitrogen. Here we go. These electrons take the H. Make bond to H, these electrons move on to oxygen, and what do we get? That becomes O with 3 long pairs, that's a minus charge. These are nitro groups, NO2. That's a common functional group, but it's not on the functional group list that I gave you. You will see a nitro group in organic 2. Very common, especially on aromatic amines. Okay? You'll eventually need to know the Lewis structure of that NO2 group, the complete bonding. This is called, what if there's no nitro groups here? What's that compound called? Well, it's called what functional group is this? Phenol. Well, that's phenol itself. This is trinitrophenol. Specifically, that's the one position, 2,4,6 trinitrophenol. It's actually pretty darn acidic. Its pK is about 1. Usually phenols are a pK of about 8 or 10. Much more acidic because of the nitro groups. We got that plus what? What else did we form here? That's triethylamine. Does that make sense? Triethylamine. 3 ethyl groups. What's on this now?
Hydrogen and plus.
Yeah, and we made a salt, an ion pair. A plus and a minus. And of course, the neutral became charged, and the neutral became charged. All these are tidbits that I gave you on the last page for information to remind you over and over. There you go. If an acid-base reaction is going to happen, that's it. Strongest base reacts with strongest acid. Okay, which side's favored? What's the acid over here? What's the acid over here? If the H was glowing in neon light, that H would be glowing. Which one is glowing over here? That's the one that was transferred. It's the acid over here. What's its pKa? pKa is 10. How do you know? Well, I told you right here. That's a pKa, which describes acid strength. Is that an acid?
No.
No, this is acting as a base. Maybe it could be an acid, but it ain't acting as an acid in this reaction. It's acting as a base. We don't use pKb's in organic chemistry. We always use pKa's. But if the thing is acting as a base, the pKa refers to the conjugate acid of that base. pKa is actually refers to this. You got to know that. So we can just move that 10 over there. Which side's favored, 1 or 10? 10, the weaker acid. This is favored by how much?
10 to the 9.
10 to the 9, which is a billion. So if you got a billion of these, after this takes place, this reaction, there'll only be one remaining. That's pretty much complete. Again, all you need is a difference of about 10 to the 3, 10 to the 2, 10 to the 3 to be complete. 10 to the 9 is plenty. Question, will triethylamine, is that strong enough to deprotonate this phenol?
Yes.
Yeah, it just did it, quite completely. Yeah? Anything else we can ask there? Looks good? How do we do on that? Okay, I suspect maybe there was a question about the pKa, but hopefully you got the reaction, yeah? Let's try the next one. I said comment on this, but I really already commented on it. I just wrote that the wrong place. See, this is just plain what's called phenol. If you have 10, it's not acidic as that. Those nitro groups make this. I left nitro group off. Where have I been already? I think I erased it. The nitro groups really stabilize this. That's why I'm so eager to form. Again, you'll see nitro groups, organic 2. Take methyl organic 2 here, you will actually do a nitration in lab. You put a nitro group on the green. What do we got here? What's the most acidic H on the board?
The only H. Or well, the OH.
You got CHs and OHs. Right here, yeah? Same thing. So this must hopefully be the base. Do we have a base? Yeah, lone pair sp2. sp2 lone pair is not quite as basic as sp3, but it's still reasonably basic. Question?
If the pKa is lower on the nitrogen group, then why is it the base?
Why is it what?
If the pKa is lower on the nitrogen group, why is it the bad? Why is it the base and not the acid?
The question is asked.
Well, okay, so if you want to call it an acid, what would be the acidic H?
That was the quick problem. Like there wouldn't be one. So.
Well, CHs tend not to be acidic.
Yeah.
Same thing up here. I mean, that could have been an acid,
Oh, that's what you were saying.
but it wasn't the strongest acid in the flask.
That's
When I say on the board, I'm saying in the flask. What's the strongest acid in the flask up here? Right there. What's the strongest acid in the flask? An OH or a CH? OH. So why are you saying this was a stronger acid?
Just based off the pKa value.
Well, the pKa doesn't refer to this being an
I
acid.
just caught on to what you were saying when you were pouring.
Yeah. If this is going to be a base, well, I'm not even looking at the pKa's yet. I'm looking at structure. That's the strongest acid. This is going to. So where's the strongest base on the board? Right here. You identify the strongest acid and the strongest base based on structure. These electrons take the H. These stay behind. We're going to get the phenoxide. Phenol oxide. It's called phenoxide anion plus what? Plus protonated, that's a positive charge. We now have this salt. This is called pyridine. Analogous to benzene, just has a nitrogen. Pyridine. Oh, nasty. Causes testicular cancer. Benzene also causes cancer. See the lab, though, so be careful with this. Which side's favored? What's the acid over here? 10. What's the acid over here?
10 to the 5.
The pyridinium, the protonate, it's 5. Which side's favored?
That side by 10 to the, or well, the left by 10.
Actually, this is favored. By how much?
10 to the 5.
Yes. Let me ask you, is pyridine strong enough for the base to deprotonate phenol?
No. because it's not.
Well, once you mix everything together, are you going to have deprotonated? You'll have some, but guess what? You're going to have 10 to the 5 of these and only one of those. That means only 1 out of every 100,000 is deprotonated. Would you consider that a good reaction? And what if you wanted to get 100,000 people to do something and you only got 1 of them to do it? Like, you really didn't do anything. The other 999,000 you didn't affect. Okay? Pyridine is actually not strong enough to deprotonate phenol. Maybe you kind of saw this in your PKAs that kind of led to that, but I wouldn't have started with that information. I would have started the way I did it. All right, so if we drew the equilibrium here and actually drew error, this side's favored, and the other side would be like that, right? Every acid base is theoretically in equilibrium. It might be a quite terrible equilibrium. Yeah? The last one. It's only one molecule. What happened? Got a whole bunch? Where's the most acidic H on the board? Carboxylic acid. There it is right there. Don't think that's it. Okay. Where's the most basic atom in the flask? Right here. It's got an acid and base in the same molecule. Mechanism. It could be internal. These electrons could take that. Or it could be, an internal would be called intramolecular. Or it could be intermolecular, where the base part of one molecule takes the acid of another. What is this ultimately going to give? The nitrogen is ultimately going to look like what? Okay, I can draw these 3 out. Sometimes we just condense it. Is that okay? NH3. Picked up a third H. Then it's going to be here with the R group. And then what's the carboxylic acid going to look like? Lone pairs. What's it going to look like? Third lone pair.
And now it's negative.
And now it's negative. And this is the result of the internal or intra. Well, I showed mechanism. I showed intermolecular, but basically it's the result of having an acid base within the same molecule. What? Is what neutral?
Yes, it is.
Because it has a positive and a negative. Or what we assume, because we don't know the R group.
What do you mean is it neutral? No, but I need to know, what do you mean by is it neutral?
I was just saying neutral because I saw a positive and a negative, and I didn't think it was neutral.
Okay. Not quite sure what you're getting at or what you're missing.
That's what I said.
Because you guys don't, we have differences, what is neutral. I think some of you think an acid is not neutral. To me, neutral is it charged or not. I've had a couple people say since it's acidic, it's not neutral. No, it's neutral. I mean, here's a carboxylic acid, it's acidic, it's also a neutral molecule. I see no charge. That's neutral. Okay. I would not recommend calling acids thinking they're not neutral or bases. Only something that's not acidic or basic you're calling neutral. I don't agree with that. Don't do that. To me, neutral, and I think you'll stay out of trouble. Neutral refers to charge. I see no charge here, thus that compound's neutral. I see charges here, but it's net neutral. When we balance, and the result, the total net charge is neutral. Okay? Yes, this thing is neutral. Now, how does it, this is an alpha amino acid. From the carbonyl, the first carbon is called alpha, and you have different R groups. You have like 20 different essential amino acids. Well, I'm sorry, the amine is at the alpha position. That's the alpha amino acid. How do these exist? Like this? By the way, what do you call this where it's net neutral but it has two charges? Anybody know that? Zwitter ion. Starts with a Z, W, that's probably German. Heard of Zwitter ion? You shook your head. You've heard of Zwitter ion? In Gen Chem or somewhere else?
No, I know.
Biology? Okay. Maybe looking at amino acids? Yeah. How do amino acids exist? Which side's favored? All neutral or this Zwitter ion form? Which side's favored? Well, what's the acid over here? 5. What's the acid over here? 10. Which side's favored? Weaker acid. Which side's weaker? No, 10 is weaker acid than 5.
Oh, yeah.
Okay, weaker acid. This side's favored. That is how an amino acid exists. It exists as a Zwitter ion. And that's another reason amino acids tend to be quite soluble in water. Not only because you can look here, lots of hydrogen bonding potential to water. You can imagine good association of this with water, hydrogen bonding all over the place possible. But if you know that it exists as a Zwitter ion, you know it's also got these sort of, it's very polarized, two different charges there. Very polar, water is the most polar solvent. Okay? Of course, that can be pH dependent. But at neutral conditions, if I just brought in an amino acid like dry, and if we could look at the molecules, they're going to look like that. Okay, what about pH? How an acid or base predominantly exists at a certain pH? We have the Henderson-Hasselbalch Equation, which tells us that pH equals pKa plus log of B over A, where B is the basic species and A is the acidic species. This is basically a conjugate acid-base pair. The acidic species is going to have the H. The basic species will not have the H. Okay. Now you got three variables here. Because this is just one variable, probably three variables. If you know these two, you can determine the pH. Or if you know pH and you know pKa, then you can determine the ratio of the two species. Conjugate acid-base pair. Now it turns out if the basic species, that's concentration brackets, right? The concentration of that is greater than A, then log of B over A will be positive. Thus pH will be greater than pKa if you work through the numbers. On the other hand, if B concentration is less than A, that if A predominates, then log of B over A will be negative. Thus pH will have to be less than pKa. Summary though. look at it sort of twisted around. If pH is greater than pKa, which will predominate? B. If pH is less than pKa, which will predominate? A. It all just comes from the numbers. Now in biochemistry, you would derive that equation. How did all that come up? How do you take basic principles and ultimately get to this simplified equation? You may do that in biochemistry. Let's use it though here. Acetic acid. How will it exist at pH of 7, which is about blood pH? Well, what are the two choices? A or B. Well, what does A and B look like? Well, A has the proton. Okay? There's the proton. So that's A. And here's the conjugate base. And the conjugate base I'm calling B, base. And conjugate base, the proton's gone. The acid has the proton, okay? Now I just described how to determine which is A and B. But all the time I get students coming in and saying, that's A because of this. And I say, hold on. No, I never said that. I don't know where that comes from. But to reiterate, how do you identify the A? As the H, right? How do you identify the B? The H is now gone. All right? So how will it exist at pH of 7? What do we need to know? We know pH. We're trying to determine basically the ratio, the B over A ratio. That's what I'm asking. Is B going to be the major one or is A going to be the major one? What else do we need to know here? You know pKa. Do we know pKa of this here? That's 5. Okay? So I've given you two of the variables. Now you can assess the third thing. What's the answer? Well, I think it's already here. Let's look at it. What do we say here? pH is greater than the pKa. B will predominate, right? Did we say that? Yes. At pH of 7, that predominates. That is, if acetic acid is in your blood, it's going to predominantly be in the circled form. Ionized as an ion. What's the ratio though? We know it predominates, but by how much? Yeah, it's 10 to the 2. And 10 to the 2 is 100 to 1. It's a 100 to 1 ratio in that pH of 7. That's 10 to the 2. It's the difference in your pKa and your pH. How do we know that? Well, that can all be derived too. It's a log relationship. At what pH does this start predominating? Tell me a pH where this would predominate. Tell me a pH where this form would predominate. 4, 3, 2, 1, 0. What if the pH was 5? Which would predominate? think I heard it.
Equilibrium. It would be neutral. The same amount would be.
Well, that's 100 to 1 equilibrium, so I wouldn't say equilibrium. I would maybe say equal. At pH of 5, it's going to be equal. It'd be 1 to 1 equilibrium, as opposed to a 100 to 1. Because at pH of 5, look at your math. If that's 5, and that's 5, what would all this have to equal? 0. Well, what do you need B and A to equal for log of that to be 0? 1. So it would be 1 over 1. It would have to be equal for that all to be, the log of that to be 0. So it all comes from your math. Okay. Okay. That's really for information there. The mic is also on the last page. Questions about Henderson-Hasselbalch? We mentioned that drugs are usually given as salts. Here's codeine. Reacting with HCl make codeine hydrochloride, more soluble in water. What's over here? Just questions you can try to answer. Just other questions. There's another acid base that you can show there. Mesylate. Instead of HCl or HBr, I'm showing this acid, which is an organic acid because it has a carbon, called methane sulfonic acid. Because this drug is the mesylate, not the hydrochloride. So there's lots of other acids that can be used to make salts or bases, etc. Okay, for information. That's the acid-base material. Questions about acid-base before we move on to back to conformation. Any questions at all about acid-base? Yes?
When you're looking at the stability, so, like the degree of acidity based on stability, how do you know when size trumps electronegativity?
You want straight down and agree. B or minus is more stable than C or minus. S minus is more stable than O minus.
So for this one, why is chlorine more stable?
Because the charge is not on the atom. It only matters, size only matters when the charge is on the atom. There we have electronegativity, and fluorine is more electronegative than fluorine. So fluorine pulls more than fluorine. Question?
Yeah, so I was wondering, you went over, I know you said earlier with we were talking about oxygen and nitrogen and oxygen being more electronegative, and you were saying, because I just want to make sure I heard you right, is that nucleus is more positively charged, so it draws in more electrons?
Yeah.
Okay.
I think, right? Is that right?
That's hard to make sure I heard you say right.
I don't think you often say that. Unfortunately, I don't like to explain things. I think you're just talking, hey, these are more electronegative, right? What does that mean? Sometimes you don't get exactly what that means, but then there's the why. Why is it more electronegative? I think it's just got more protons. That makes sense, right? And then physics takes over. The more protons, the more strongly it's going to pull up electrons. And then at that point it becomes duh, almost, right? Does that make sense? Get a lot of protons, if they're going to pull a minus one. I don't quite get as an instructor why that's not mentioned in. Any other questions about nested base? Take a short 2-minute break then, and then we'll pick up with confirmations.
It's been like this for years. Straight up, it's been like this. You check our confirmation.
That's right. You've got all the bonds coming out the back front. Front carbon is small one. Small one. You don't have any bonds coming off the small one.
Oh, I'm sorry, I mean.
No, here you do.
Yeah, that's right.
I'm gonna have to go through it, and I can't just put that across right. I have to do it, so let's actually do it. Go to the cut. I can see things like that.
The least one that I got was the box, that's the least complicated.
You have what? What do you mean lease?
Or your question
What,
is
stable?
basically,
Well, it's energy, which one? Why you call it those?
this one, because I was doing I was counting the Dosh, or Dosh, that you got and whichever had the lower.
You get the lowest by having the biggest groups ante.
Well, I saw a lot of, I mean, all three of them had antics when I did. Unless I'm understanding wrong.
No, biggest groups ante, there's only one way to have biggest groups ante. Right? Are your biggest groups ante?
Yeah, the biggest groups are.
They don't look ante to me.
Does it matter which plane you rotate when you're looking at it? Doesn't? Okay. And then also, I know you're going to go over it, but so I labeled or numbered this one starting on this end 1, 2, 3, 4, 5. But then last week's lecture you labeled it 1, 2, 3, 4, 5. And that would change the whole.
Yeah, one over here. Here you have one subject and two.
Right.
If you come the other way, you'll have two subjects and two. And that's better in terms of nomenclature.
Okay. Okay.
I mean, like, that's either
What about like if you leave from, I guess, this way, like in front of the paper, or I should say?
Well, if it's in front, it'll be on your left.
Okay, so
If
it
it's
was
behind,
on,
it'll be on your right.
so it was on this side. Because then it would be vice versa, you know what I'm saying?
If something is coming in, I'm gonna do that, off the paper. If you want to look at it like that, it's on your left. Isn't that to your left? Well, if you look at it this way, it's on your, yeah.
Okay, cool.
However you want to look at it.
Okay.
Yeah, that's a good way. Back turning your paper is good. That can't turn forward.
Yeah.
Right?
I was just making
I
sure
have to
I
get up
was
there and stand.
looking at it right, how you were saying.
Turning the paper, I do that in the paper, yeah.
Okay, cool.
What? I mean, yeah. Okay, guys. Let's look at confirmations. Then we did the first one here. Let's do the next one, is looking down the 2-3 bond. What's 2? Nomenclature, this is 1, 2, 2, 3. looking down that. That is down to 2, 3. 2's in front. 2, 3. For the 2 to be in front, which side do I need to stand on? Over here. Can you see me looking down the 2, 3 bond? Okay. Now, we just talked about paper here. There it is on the board. See, I can do that this way. There it is. But I'm going to turn it. Now it's like it's on the board. Here's the board just moved out. Now I'm over here, like right there, and I'm looking down the 2, 3 bond. Okay? So that's me looking at it up there. This is me looking at it in real life. You can turn your paper. Now, you want to hold your paper like this? Looking down the 2, 3 bond. Now the bromine. Now the bromine is bolded. That means it's coming up or out. Right? If this is like that, it's going up. If it's like that, it's coming this way. If I'm over here, the bromine's coming out, it's on my what? It's going to my right or left? Go to my right. Okay? I'm just going to do it up here, but that you can do it by looking down your paper. But this is me looking down the paper. Then the board is the paper. I'm holding it up there, flat like the board, and I'm looking down. But I see the bromine coming this way. And I want to draw what I see. Well, I can't draw it here because that's air. But I can draw it on my paper. What do I see? I'm drawing what I see there. I see a bromine going out. It's also going up and to the right. What's on carbon 2 going straight down? I need to get another and if I hold it like this, looking down the 2, 3, carbon 2 has something that's right down the paper. It's not going forward or back. What is that? This methyl group is coming right down the paper. It's not going forward or back. Looking straight down to my feet. I'm going to draw in a methyl just to clarify that's a CH3. What's on carbon 2? I hold it like this. What's on carbon 2 going this way?
Hydrogen.
Undrawn hydrogen. If we drew it in, it would be dashed going back. If I'm looking at it here, and undrawn H is going back, that's to my left. Okay, back carbon. Looking down to 2, 3. I see that back carbon over there. I see something going straight down into paper, straight down into board. What is that? What's going straight down off carbon 3?
Ethyl.
Ethyl group. See it going straight down? Is that ethyl group going back or forward? Neither. It's going straight down in the plane of the board. Uh-oh, this methyl's going straight down. It's eclipsed with the methyl. We're going to do that, though, like this. Just a little bit to the side. There's the ethyl. What's on carbon 3 going back behind the paper? I see a dash. Dash means it's going behind the paper. This is the front of the paper. What's going back on carbon 3? I'm looking at it going back to my left. It's also going up a little bit. That's a methyl. It's actually eclipsed with the H. What's on carbon 3 to my right? I see the methyl going back. Is there anything coming out? Undrawn hydrogen would be bolded. We drew it in, right? We drew in the undrawn H. Wouldn't it be that? Because it's tetrahedral. 2 in the plane, 1 forward, 1 back. We drew in the H here. be one back. 2 in the plane, 1 forward, 1 back. So if I'm up here and the H is going back, to my left, that one. But this one, if I'm up here, that H is to my right. I'm just drawing what I see, but I'm doing it here, to my right. That H, the H is actually eclipsed with the bromine. Do it like that. There's the conformation as originally on the board. Is that the best conformation? No, eclipse is never the best. What's going to be the best? Aaron? What's the total best conformation we want to draw? What groups do we want to put anti? Biggest group on the front carbon? Bromine. Biggest group on the back carbon? Ethyl. These need to be anti. What do you want to rotate? It doesn't matter, front or back. I'm going to rotate the front. No, actually I'm going to rotate the back. It don't matter at all. I'm just trying to see which might be easier. If any of them is easier. What did I say? The back? The front's the same. The front is the same. The back, we're rotating. We want the ethyl to be here, anti to the bromine. This just turns like a clock valve. If the ethyl moves here, where does this methyl move? It's going to be straight up. And what else is on the back? I'm drawing H. Yeah. Now in Newman's we do draw in the H's. Okay, we do draw them in Newman conformation. So is that the best? We got the bromine and the ethyl anti? Yes, we said that's the best. There you go. Now it's in the best conformation. We've gone through the process. And now we can answer questions like this. What's the dihedral angle between the bromine and the methyl? Dihedral angle between the bromine and the methyl is 60 degrees. Uh-huh. What's the dihedral angle between the two methyls? 180. Yeah? Which groups are gouged to the ethyl? Okay, so now we can ask questions like this. Looking at the best conformation. When the molecule is in its best conformation, we can now discuss it. Because, guess what? This is equilibrium. I mean, I don't know if it's true equilibrium, but of all these possible conformations, which one is most likely preferred? That's what we're doing, this one. So when this guy's hanging out, or gal's hanging out, you know, on a Saturday afternoon or something, the bromine tends to be mostly anti to the ethyl most of the time.
It's like a very high energy conformation.
High energy?
Yeah. Just things are still gauge and that's still a lot of energy. Methyl and bromine.
Well, but you said it's high energy. It's the
It's
best.
not- It's the best, but it's not.
It's the best. We're not saying absolutely how good it is. We're just saying it's the best
Yeah.
of the possibilities. I mean, yes, you still have some groups that are gouged right here. Ethyl and methyl gouged. But guess what? If you move the methyl over here, then you got the bromine next to the ethyl. And that's worse. We've got a complex, actually not too complex. Looking down the 4-3 bond. In nomenclature, this is 1, 2, 3, 4. Okay? Because this, if that was 1, you would have only one substituent at the 2. But this way you have 2 methyls at the 2. Lowest, that gives you lower subs. Because ultimately a 2, 2, 3, 4 is better than a 2, 3, 4, 4. Which subs have lowest numbers? Right there, right? Looking down the 4, 3. 4's in front. So we want to stand here. And what do we see? Circle, circle, dot, dot. Okay, over here. Again, you can turn your paper, hold it like it's on the board, but you're standing over here. Look down the 4, 3 bond. I'm going to make my bond sort of flat so I can look straight down. I'm looking down a road. I can see with my left eye there. The front carbon, I see something straight up. I'm just going to look here. I see a methyl straight up. I'm going to clarify it as an ME. I see an iodine coming bolded, so it's coming off the paper. This is the front of the paper. Iodine here, is that right? Iodine to the left. But it's also going a little bit down compared to the carbon. Everybody agree? Also on that front carbon, I see, well, nothing else, but there's an undrawn H going the other way. And that's to my right. It's coming behind. It's dashed if I drew it in. To my right. It's also going down if you draw it in. Tetrahedral nature. Let's look past that to the other carbon over there. That other carbon, I see something going straight down into paper. What type of group is that? We call that common group. Terbutyl. Terbutyl group's going straight down. On that carbon, there's something, a methyl bolded, meaning it's coming off from the paper. If I'm over here, that's to my left. It's also going a little bit up. And what else is on that carbon? Undrawn H. It's going the other way. Is that the best? No. No. Right now, you have the two biggest groups. Gauche. Let's rotate the front. Let's put the iodine anti to the terbutyl. Circle, circle, dot, dot. Iodine straight up. Methyl moves here. H moves here. The back is the same. H there, methyl there. Terbutyl down. Here's the best. Terbutyl and big iodine are anti. In the best conformations, the methyls are what? Methyls are also anti. Right? A variety of questions that could be asked. So that's what we're doing. We're learning how to draw them, assess them, and terminology. Is anti always the best? Well, there's exceptions to just about everything. Here's an exception. If you look at this compound, 2 carbons, each one has an OH. It actually prefers the Gauss conformation. The OH is a bigger group than just a H. So the OHs are in bigger groups. They're not anti. Why is this preferred? Well, then I'll have to say, well, why is it more stable? What did I just illustrate there? Hydrogen bonding. Which is a good thing. These groups are anti. They're like, you know, ooh, all right, hydrogen bondings. The oxygen's like, ooh, I like UH. Is that a covalent bond? No, it's a non-covalent interaction. It's an IMF. This is a pretty strong IMF that makes this conformation favored. Make sense? Yeah? Okay. showed some hydrogen bonding up there, but it was with a Newman. You don't always have to show it in a Newman. Can you show by the way, what type of hydrogen bonding did we do up there? It was internal, intramolecular, right? So we could show that. And you could show this, you don't have to draw Newman to show that. Let's do it down here. Can you show an intramolecular hydrogen bonding down here? See a possibility here? How about that? Does that illustrate an intramolecular H bonding with this compound?
Pi bonds can't rotate.
No, I rotated this bond. That's the bond I actually rotated. No, that's not the bond I rotated. It ended up moving. The bond I rotated was actually here. You got a model, that's what's rotated. As you turn that bond, this group is going to come down. Okay? Did not rotate a pi bond. You'd have to think about that. The main thing here is I'm showing an intramolecular hydrogen bonding. I just don't want to think you have to always show a Newman. This is just kind of rotating your compound without doing a Newman. We don't need to do a Newman. All right? You know the difference between intra and inter? An interstate goes between two different states. Intermolecular is two different molecules. This is within the same molecule, called intramolecular. Yeah? Okay, with Newmans you do need to be able to go the other way. Anybody got a name for this first one here? Can you name that compound? Well, let's take it back from a Newman to a more traditional line bond structure. I would recommend doing that. I got a front carbon, and I'm going to draw in the C as opposed to a dot. What's on the front carbon? Okay. If I'm looking at it, I see a methyl going straight up. Everybody agree? The methyl going straight up is going to be sort of like over here. Like me standing over here. I'll put the two carbons here. You're looking straight down. For me to look straight down, I'm going to draw it like this. Methyl straight up. What else is on the front carbon? Bromine? You're looking at what I'm looking at. What am I looking at? The bromine is on my... I'm out there with you. The bromine is on your... Right. Bromine's on the... For the bromine to be on my right, do I need to draw it dashed or bold here?
Bold.
It needs to be on my right. It needs to be bolded. The other thing is what? The butyl group? It's dashed. We dash the first carbon, then we do like that. Okay, look in the back, on the back carbon. Is there something going straight up or down? And then we have an F. Which side's it on? Okay, for it to be on my left, I have to draw it dashed. And what else is there? Another H. Okay, another H. It really doesn't matter. If we drew it, it would be bolded, but it doesn't matter because it's not chiral. We'll learn that during test 2. There you go. There's the compound on. See, what we've done before is we went from here to there. We just went backwards. Okay? Now you can name the compound. You want to clean this up and make it just a nice line bond? What do we have? Carbon, carbon, carbon. Well, I'm not going to do that. I'm not going to do that. You might do that. We got a little stereochemistry here that you have to think about a little bit. How to draw it. You should be able to name it right there, right? What's the longest continuous carbon chain? I actually see 2 6s. So you're going to have to decide which 6 is best. Is that right? You should be able to name it there. Work on those 2 and we'll look at them next week on Tuesday. Yeah? Okay, last topic for test 1 material is cyclohexanes. Cycloalkane. But the only one we're going to look at is cyclohexane. Most common. And we're going to look at the sort of the conformations of it. I have here a cyclohexane. And if we draw it on the board, it just looks like that, right? All right, saturated, no pi bonds. Is this ring flat on the board? Is all that flat? I mean, like this paper, is this paper flat on the board? Yeah, nothing coming out of the back. What about that ring? Is it flat on the board in real life?
No.
Why no? Michael? Yeah, what's hybridization of each carbon? Geometry, I mean. Tetrahedral, and how do you describe a tetrahedral? 2 in the plane, 1 forward, 1 back. So if something is forward in the back, it ain't all in the plane. Something is forward and back. Yeah, that's one way to look at it. What about the carbons though? Are all the carbons in the plane? Well, the answer is no. Because if it was, just the carbons are all flat there. And if they are all flat on the board, then you see the H's are on each side. So that right there. But what about the carbons? Are they flat? Is the ring flat itself? And the answer is no. Because, a couple of reasons. One is, if it was, how would neighboring hydrogens be? There are neighboring hydrogens. What would they, how would you describe them? Because I can't see the ones behind it. They are eclipsed. If it was flat, the neighboring hydrogens would all be eclipsed. Is that good? No. Also, if you go to 9th grade geometry, I think a 6-membered ring is going to require bigger angles than 109.5. I think it's actually 120. I don't know. But these carbons want what type of angle? They're all sp3. 109.5. How can we get it? Instead of it being flat, the ring puckers. One end turns up, and the other end, well, if both ends are up, now we see the ring's not flat. 4 are in the plane and 2 are forward. Okay? Now what did that puckering do? Now look at neighboring hydrogens. There's 1 and there's 2. Are they eclipsed? They're no longer eclipsed. That puckering relieves that strain. Okay? And it turns out that the puckering now makes these bond angles more like 1 and 9.5. It exists puckered. There's two ways to pucker though. Both ends can be up or one up and one down. If one is down, you have 4 in a plane, 1 forward and 1 back. 4 in the plane. Plane being through there. Okay. With both of them up, both ends up, that is called a boat conformation. Kind of like an Italian gondola with the ends both up. That's kind of where that comes from, a little classical Italian boat. All right? Now the boat, this is the last time we'll ever talk about it. The boat is not the best. Main reason because when it's up, these two H's up here, okay, or if it's two groups, those groups up there, they sort of clash. But even if it's just hydrogens, even though they're small, they clash. And it's better for one end to be up and the other to be down. And now those groups aren't clashing as much. They're away from each other. And when one is up and one's down, we call that what type of conformation? Not a boat conformation, but it's called a chair conformation. It's like you're sitting here and you have your back up, and then maybe you have a leg support going down. And sit here. And you sometimes see pictures of some cartoons sitting here. The back of the kids here, looking at the ocean. Okay. So chair conformation is better than boat. Now we're going to look at chair conformations, how to draw them, and have discussion there, terminology, questions like we did with Newman's. You don't do a Newman with a cyclohexane, you draw a chair. How do we draw that on the board? Okay, a couple of things I can say about this first. First off, if it was flat, which it ain't, it was, and I set it down, it was flat there, how many H's are hitting the table? Okay? Imagine if this hit the floor. How many of those H's would hit the floor? All 6 of them would. But if we go to a chair conformation, and this hits the floor, I'm going to lean it so you maybe see the floor. How many are hitting the floor? Yeah, only 3. See, only 3 are straight down in the chair conformation. What about straight up? How many are straight up? It's actually 3, because if I turn it over, how many hit the floor? 3 are now hitting the floor. The ones that are straight up or straight down are called axial. 3 up, 3 down. That's only 6. This molecule has 12 H's. The other 6 never are not straight up or straight down. The other 6 are all projected to the side, like around to the side. They're all around in this volume. Okay? Like the equator is sort of around, but it's not like at the pole. The pole is like the axis. Axial. The equator here, that's right. And these H's that are around the side here are called equatorial. Equator. Equatorial. Okay? Look at my model right here. Is the red axial or equatorial? Axial, straight up. The red is axial. How about the blue? What is it? The blue is equatorial. Okay? All right, let's draw a chair conformation. There it is there. And we just draw it like that. Okay? But that's like drawing methane with just all the bonds there. Not really showing the tetrahedral nature. You can draw it like that, but you're not showing the full chair conformation nature. Here we go. Thanks to do it. Y'all ready? Y'all find study groups to be helpful? Friday afternoon is a good time for maybe a study group. Yeah, no lab. Make use of your Friday afternoon, I would recommend, okay? The next 4 or 5 Friday afternoons. It's a good prime time for getting stuff done, yeah? Study groups. If you like study groups, sometimes it's better to study along, because depending on what you'd like to do. Or maybe a little bit of both. So study along, get together, discuss. Okay, let's do chair confirmation. Here we go. We need 6 carbons, all right? We draw 2 there and 2 here. Sort of parallel offset like this, yeah? That's actually 4 carbons. Then we're going to connect these 2 with a point like this. Boom, boom. Over here we're going to do the same, but we're going to come down. Boom, boom. Okay? You get that? We'll do it again. It's not always going to look perfect. This one's good enough. Let's draw in the H's though. Each carbon has 2 H's, right? Yeah? 2 H's here. How are they? We can hold this. Every carbon has an axial bond and an equatorial bond. How do we draw that? I call these up carbons. There's 3 carbons that seem to be sort of up. That one, that one, and that one. Up carbons get straight up bonds. And here, since everything's H, straight up H, straight up H, straight up H. Do it like that. Sometimes this H may be drawn longer, and you sort of put it above that line. Okay. Down carbons, which are down, down, and down, these get straight down bonds. And we can draw these in like this. Up carbons get up H's, down carbons get down H's or down bonds. It could be a chlorine or the other things. Those are your 6 axial H's. 3 up, 3 down. Now each carbon also has an equatorial. How do you do this? It's going to come over to the side here, but what exactly, don't do this. That is not really appropriate. This bond needs to be parallel to not these bonds, not this bond, but one away. This bond is going to be parallel to that carbon-carbon bond. And so you draw it like this. See how that and this are parallel? This bond is going to be parallel, not to that, the first carbon-carbon bond, but the next one. And it goes this way. And it's going to be like that. Do these look parallel, close enough? This one, can you draw in that one? Draw that equatorial H in. Not parallel to the connecting carbon-carbon bond, but the next one, right? Either way you go, because you see these 2 are parallel. Either way you go, you get the same line. We'll make this parallel to that, and so we need to come up like that. Is that right? But see, is this H here up or down? Well, oh, I'm sorry, that little vague question there. Is this H axial?
No.
No, that's the axial H, straight down. This is not straight up or straight down, it's filling the side volume. Right? This one over here would be not parallel to that, but the next. And you see actually this or this. And so it comes like this. And this one here. This one here, depending on how you angle this, it almost may look like it's straight up, but it's not supposed to. That's a straight down. The other one is a little, needs to be like this. So that's actually equatorial. Now this is supposed to be also 3D to a certain degree. If I held this here, I wish this was bigger. I'll put this here. I wish these ends were just bigger to come up more. But that's how it is on the board. And aren't these two carbons closer to you than these over here, which are further away back? You got to kind of see that. This is supposed to be sort of closer to you, and that's sort of in the back, and it's sitting here sort of 3D. You see the red H? Which one is red? Can you put your pin on the red H? Straight up axial? What about the blue H?
Wait,
That's supposed to, see the model is a little small. It's over here. This is the blue H. That's the red H. Okay, let's see what we need to do here. You'll see ring flip. Okay, ring flip.
I forgot one of the H's.
Did I? Which one? Right here?
Yeah.
Let's put it right here. You'll read about ring flips. A ring flip is where, what can this thing do? It can't rotate. If you rotate it, you're going to just destroy their model in your ring. Okay? It can't, the ring keeps it from rotating. Right? You see that? Okay. What can it do? It doesn't have any mobility, flexibility. Yes, what can happen with these, first off, they can do this. And you see advanced readings, you'll see like twisted boats and stuff. I'm not taking this there. We're just going to go from one boat to the other. Let's focus on, let's keep going. Right now, okay. What can happen is, this can flip up, and the other can flip down. And that's sort of your mobility. All right? And that's called a ring flip. And the ring flip is going from, well, for me, for what we're going to do, it's going from one boat to the other. I'm sorry, not boat, from one chair to the other, right? What happens when we do a ring flip? Right now, the blue is axial, and the red is equatorial. Let's do a chair ring flip. This here, this here. Now the red is axial and the blue is equatorial. That's important. Anytime you do a ring flip, your axials go to equatorial and your equatorials go to axial. Okay? For example, if we start this here, and we do a ring flip, we pull this end down, okay? Pull that end down, and we push the other end up. And this goes up. How do we draw that? You know how I started this one? I drew two lines like this. Instead, we sort of draw them the other way, sort of mirrored, and we draw it like this. Now, I'm not as good as drawing this one, so it may look a little. Usually I just draw that one and I'll show you. But we just connect them. Boop, boop. That can be a little bit more pointy. And we connect here, is that right? Let's start this one here as well. We can draw our H's. That's a straight up carbon. That's a straight up carbon. That's a straight up carbon. Straight down carbon. Straight down carbon. Straight down carbon. Here are your axial H's. Then we can put in the equatorials. Yeah. Parallel to that. 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 And that needs to be parallel to that. It's almost coming straight down. Maybe not. Did we get them all?
Yes.
Okay, since we have two, we'll call that one, and this two. How about that instead? Where's H1 at? Put your pen on H1. Where's it at now? Same molecule, we just did a ring flip. We just did this. So, right here, yeah? The axial H is now equatorial. Okay? Right? Here it is over here. This H is straight up on that up carbon. All right? We're just bending it down and pushing this up. Now it's like that. Now it's over here. And there it is. An H straight down, and this H is equatorial. I know some of you can't see as well as others. Where's H2? It's that H up there, yeah? Look, I did the ring flip. The H is blue. Can you see that at all? I can't tell what you can see because under the light. Because of the blue, that's it. It's now axial. This carbon now an up carbon. You seeing it here? Let me ask you this. Are the two H's we're looking at, are they cis or trans? Are these two H's cis or trans? Wait a minute, what does that mean? Remember we looked at disubstituted cyclohexanes? What is cis? Both forward or both back. What is trans? Okay, are these cis or trans? All right, if I drew it on the board flat, there it is on the board flat. There it is on the board flat. And the H's are red and blue. Are they cis or trans? What if I hold it like this? Okay, easy. Needs to be easy up here as well. Are they cis or trans? Well, you know the answer because it's the same as I got in my hand. They're cis. How do we know they're cis? How do you look at them and tell they're cis up there? Because another way to draw this is important because you need to be able, here's what we draw this. How would we show that They're cis here.
So it's 1, 4.
Okay. Now pretend they're bromines or something that makes it relevant, different. Is that it? They're cis? Are these the two H's drawn in, right? Tell me again. This is it? Why are you saying no?
Because they would be the same flavor. Because that's 1, 3.
Thank you. Thank
It's
you.
supposed to be 1, 4.
This is a 1-3 relationship. Are they in a 1-3
They're
relationship?
in a 1, 4 relationship.
If that's 1, that's 2, that's 3, that's 4. They're 1-4. No, I'm just making a mistake so you can see how not to make mistakes. We want to draw it here. Here's the same compound we're dealing with, just drawn in a standard perspective drawing that kind of looks flat, but it is indicating the cis nature of these two. Please don't be confused with these being H's and it leading to sort of like what? Assume they're bromines or something. That would get rid of that if you're thinking that. Okay. How do we know they're cis? Can anybody tell they're cis in my drawing over there? That's what. Okay. That's how we introduce it. How do we know they're cis here? Well, you look at this. You look at the two things here. H's or chlorines or different things. Okay. This is above the other thing. That H is above that one. Okay. All right? That H is above the other one. How about this one? Compared to the other one. They're both above the other thing bonded to the carbon. So they're cis. Okay? Let's do it over here. These two H's, are they cis or trans? Those two H's are? Those two H's are cis. They're both above the other thing on the carbon, right? Could you, if those were bromines or something, could you draw that like I did over there? Cis, okay. What about those two H's, cis or trans? I hear trans. Anybody say cis? No? Those two H's are trans. And if we drew them in a perspective drawing, we would draw one dash and one bold to indicate that. Those two H's, okay? All right. Let's do some here. Are the two halogens cis or trans? Now I'm not drawing in the H's here. If you drew in this H, it would be straight up, right? And this H would be straight down. What are they here?
One's global.
They're all cis or trans? Okay.
Trans.
Yes, they're trans. And thus the molecule is called trans because the halogens are the business part of the molecule. Right? How about the next one? Are they cis or trans? Good. Straight down H, straight down H, they're cis. Could you draw this molecule in a perspective drawing like I did over there? should be able to. This one here, cis or trans?
Trans.
That's that. This is this. Chlorine's below the H. F is above the H. They're trans. Can you name that compound we just looked at on the end? Name it fully. Name that compound. Fluorine is spelled with a U. Fluoro. Yeah? But we're going to put trans in front of it. Trans is a stereochemical descriptor. Because that name up there, you could also have cis. The two groups could be cis, and that's two different compounds. They're stereoisomers. You need to put trans there. We identified it as trans. Yeah? That's a stereochemical descriptor. We didn't talk about it. Ring flips. The preferred space for a large group is equatorial. There's more room equatorial. Equatorial is your best position. If we look here, you may not see this with the model, but axials sort of interact negatively with the other two axials. Because the model, these are small. But imagine if it was sort of big groups up here. If it was a big group, this here would be right next to these big groups. Okay? That's actually called 1-3, because that's 1, 2, 3. 1-3 diaxial interactions. And that's not good. It's best if this is going to do a ring flip. We focus on the red. If you look equatorial, there's just more space out here for that group to be. All right? Equatorial is the best. You can see that with such here, it's known, this can be measured by some analysis or something. Cyclohexane with one methyl cyclohexane. Which conformation is preferred? That, with the methyl equatorial, because it's bigger. And we know that it's an 18-to-1 ratio sort of at equilibrium. All right? Preferred. But look at this. If that one group is a tert-butyl group, it's preferred 4,800-to-1. Why does a tert-butyl favor that so much more?
It's so much bigger.
Because it's bigger. A tert-butyl is like, I've got to be equatorial here, and I'm staying equatorial. I'm not going to kind of bounce back and forth at all. Okay? Equatorial kind of fixes that conformation more to does not want to do a ring flip. But enough of like, well, I'll do it once in a while. But, okay? So what if we had two groups? Which conformation is preferred, left or right? On the left, correct? Because it has the biggest group equatorial. Humans, we said biggest groups anti. Well, here you want biggest groups equatorial. Homework. Show each of the following lowest energy conformation. Now, I could have clarified lowest energy chair conformation, but you see these are cyclohexanes, so you know we're doing chairs. Right? Can you do the first one? And then I'll let you do the other one on your own. Show that in the lowest. Lowest energy chair conformation. Okay, on Tuesday we'll look at IR a little bit as necessary. After we have a quiz. Okay? And quiz will cover everything up through all the handouts, everything. In preparation. This is the end of the material right here, I believe, for test 1.
Quiz on Tuesday.
Anybody got it? Want me to do one course first?
Yes.
Okay, how about a chair? How about a pen to write? That's kind of ugly. Yeah? Okay. This is the way I do it. Where you want to put the chlorine, or I'm going to say bromine first. One bromine. Where do you want to put bromine in? It don't matter. It doesn't matter where you put the first one. It only matters where you put the second one compared to the first one. This is a relative position. Okay, I like to start right here. Which group do you want to make sure becomes equatorial? Bromine's bigger. I tend to want to put bromine equatorial. Now, I do have to be careful about so-called enantiomers, and I may try to do that, or I may end up with an enantiomer, but it doesn't matter for us right now. We'll cover that in test 2. I don't want to have to talk about that now. If I end up getting it wrong, it's okay right now. I'm not going to worry about it. 50-50 chance almost that I may get it wrong over that, but okay. I think I'm going to get it right, just so when you look back, you won't say I got it wrong. I'm going to put the next bromine. Where do you want to put the next bromine? Well, the next bromine is right next door, right? So we can't put the next bromine here. We would be wrong. The next bromine has to go either here or here. Okay? But I'm actually going to put it here because I know a little bit. Let's put the next bromine here. Here's the question, though, for you. Should we put it axial or equatorial?
Because it has to be going in the
Well, the
same.
bromines are cis. Everybody agree? For it to be cis, do we want to put axial or equatorial?
Let's go axial.
No, it would be axial. Okay. Are the two bromines I have up there cis?
Yes.
Yes, they're supposed to be cis because we're drawing that compound over there. There we go. Where does the fluorine go? Here?
No, it has to go on that next.
actually put it here or here, and it would be a 1, 2, 3 relationship. But I know something that you don't know. I think, if I'm seeing it correctly, I'm going to put it here. We'll step back and see, is it the same compound? Here. Should it go axial or equatorial? Well, it's trans to both bromines. It needs to be trans to that bromine. For it to be trans, we want to show it equatorial. Now, I ask you always that when carbons have substituents, let's draw in the H's. Draw in the H's. I'm not going to require you to draw in H's over here, but business sense, let's draw in the H's. Yeah? Is that the same compound? First, let's make sure it is. Is it 1, 2 bromine, 3 fluorine? 1, 2 bromine, then the 3 fluorine? If we consider it like that? Are the bromines actually cis here as they're supposed to be? Yes. Is either bromine, or is the bromine in F trans? Because each bromine in the F are trans. Are these trans? Yes. Bromine's down, F is up. Trans. We got the right positioning, 1, 2, 3. It's not 1, 2, 4, is it? No, it's 1, 2, 3. And everything has the right orientation in terms of cis trans. There it is. Is that the best conformation?
No.
Or do we need to do a ring flip? Let's do a ring flip real quick. Let's pull this end down, and let's move this end up. That would be not like this, but like this. Is that right? That point actually comes down. Bromine here. Let's call that bromine 1, and that's bromine 2. Bromine 1 comes here. Bromine 2 is going to be up here. We're going to draw in the H's. And the F comes here. Does that change the molecule any? Is that still 1, 2, 3? Are the bromines still cis, they're supposed to be?
Yes.
The bromines are still cis. Is the bromine and F still trans, either one?
Yes.
Yeah. It's the same compound, we just did a ring flip. We didn't mess anything up. Did bromine 1 go from equatorial to axial? Did F go from equatorial to axial? Did bromine 2 go from axial to equatorial?
Yes.
Yes, that's a ring flip. The question is, which is favored? Left or right? Well, there has to be one. One is favored. Which one's favored? This is favored. Why?
Doesn't have diaxial.
The bromine positioning is the same in both. One is equatorial, one's axial. One is equatorial, one's axial. So that's like a wash. That doesn't give you the answer. So you have to look for something else to give you the answer. What about the fluorine? At least over here, the fluorine is also equatorial. Would you rather have one bromine each way in the fluorine axial, or one bromine each way in the fluorine equatorial? That way. Here's one thing students often try to do here. I'm going to put both bromines equatorial. This compound, they can't both be equatorial. Now if you change one of these to the other projection, that is, if you change the first bromine to the other projection, that one, if you made that dashed, then they could both be equatorial. But that's a different compound. That's a different stereoisomer. Okay, do the other one on your own. We'll see you on Tuesday. Make use of your Friday afternoon and also have a nice and safe weekend. Tuesday, I sent out the